Good afternoon, everyone. In our previous class, we looked at fundamental and derived quantities. So, quantities were classified into fundamental and derived. But today, we want to look at another way of classifying quantities. Physical quantities can be classified as scalars or vectors. So, what do we mean by that? A physical quantity that has only magnitude is called a scalar quantity, while a physical quantity that has both magnitude and direction is called a vector quantity. What do we mean by it has both magnitude and direction? Yes, there are some quantities, if we don't mention their magnitude and direction, they will not pass a complete sense. For example, if I tell you, if you get into my office, take 5 steps. The question you're going to ask me is, 5 steps in what direction, sir? Because you can't just take 5 steps. You don't know whether it is 5 steps to the left, or 5 steps to the right, or 5 steps ahead of you. So you need to ask. So the quantity of taking 5 steps is a displacement quantity in physics, and displacement is a vector quantity. So a vector quantity requires both magnitude and direction to be fully what understood. So let's go to the next page. Let's go to the examples of scalar quantity. Sorry, this is typo. It's not scalable. It's scalar quantity, scalar and vector quantity. So on the first column, we have the vectors. On the second column, we have the scalar. So displacement is a vector, mass is a scalar, velocity is a vector, length is a scalar. So the best way for you to identify scalar and vector quantities is by ensuring that when you come across new quantities in physics, whenever you come across new quantities in physics, make sure you know whether the quantity or the quantities are vector or scalar. Let's assume now you are doing work, energy, and power. You have to know whether work is a vector or a scalar. Work is a scalar quantity. Energy is a scalar quantity. Mass is a scalar quantity. But force is a vector quantity. That's how you learn it. It's not by piling up all quantities in physics and separating them into vector and scalar. That will be very tedious for you to learn. But as you get into new topic after new topic, and you come across new quantities, you start learning whether they are vector or scalar. That's very, very important. So let's move ahead. There's something I want to tell you here that's very, very important. You can see electric field strength. Electric field strength. It's a electric field strength. You can see whenever you have any field, and they're talking about the strength of the field or the intensity of the field, please, it is a vector quantity. Please, it is a vector quantity. We are talking about magnetic field strength, it's a vector quantity. Electric field strength is a vector quantity. Gravitational field strength is a vector quantity. But whenever they are talking about potential, whether electric field potential, whether gravitational field potential, it is a what? A scalar quantity. Because whenever I want to define potential, we define potential as the work done. So talking about electric field potential is like we are talking about work done. And work being a scalar means that electric field potential, which is defined in terms of work done, will also be a scalar quantity. Please take note of that. And also take note of this. Here you have a force. Force is a what? Vector quantity. Any type of force at all. Friction is a force, then it is a vector quantity. Weight is a force, it's a what? It's a vector quantity. Gravitational field is a force, it's a vector quantity. So any force at all is a vector quantity. So that's how to strategically learn vector and scalar quantities. Now let's go to very important property of what? Of a vector is that a single vector can represent in effect several vectors at a point. What do I mean by this? if I put a box here now, and this box, I ask the student to push the box along this side with 5 Newton, and I ask another student to pull the box with 10 Newton. You can see, instead of asking one boy to pull by 10 Newton and the other one to push by 5 Newton, I can just ask either of them to what? To push by what? 15 Newton. You can see these two forces are acting at a point, and in effect, they are applying a force of what? 15 Newton. So this is a single force that represents these two forces acting at a point. In effect, take note, in effect, because sometimes you can see that the magnitude is different from the magnitude of the two forces, though they are still in the same direction, but it's not every time that they will be in the same direction. We are still going to we are still going to be very clear about that as we progress. So, what is a resultant vector? Resultant vector is a single vector that represents in effect, take note, it is in effect, not magnitude and direction, several vectors at a point. So, there's another property of vectors that we need to add vectors together. How do we add vectors? Unlike scalars, we can just add them the way we add our 3, 4 plus 5, 5 plus 7, the way we do addition in mathematics. We call that algebraic addition. But for vectors, we have ways, strategical ways we normally work, add them. And the way we add them, they are governed by two basic laws. The first one is the triangle law, and the other one is what? Parallelogram law. In the real sense of the idea, both triangle law and parallelogram law are talking about the same thing, and you're going to find out very soon. Now, let's look at triangle law. Triangle law says that if two vectors are represented in magnitude and direction by the two sides of a triangle, taken in order, the third side, taken in order, the third side taken in the opposite order represent the resultant force, the resultant vector. Now, what does it mean? What's the meaning of this exactly? Good. What they're trying to tell us is that when you add two vectors together, or more than two, the vector that you get, that single vector that you get, is the one that we call resultant vector, which is going to represent all the vectors in effect. Now, let's look at it. The triangle law says that if you have a triangle like this, and we use the two sides to represent what? Vectors. Look at it, taken in order. Can you see the arrow of this one? This A, look at the arrow of this A. Good. Look at the direction of that arrow. And look at the what? Arrow of this B. Look at the arrow of this B. Can you see that the arrow of this one is coming from here? And it's like it can also take this direction. If you take this direction, you can see it. If you take this direction, it will still match. It will still be in accordance with the direction of B. So A and B are vectors that are represented by the two sides of what? Of a triangle, taken in order. Taken in order. You see, the third one, if you continue with this, if you continue with this, okay, let me rub this. If you continue with this, now look at it. If I try to use an arrow to show the direction of flow, look at it. Can you see that when this vector gets here and trying to be coming to this side, it's going to contradict the other third side? Yes, because the law says that the other side is taken. If the other side is taken in the word opposite order, then it represents the word resultant. So this is the resultant of the two vectors. So the vector whose direction contradicts the other two directions is the resultant vector. Take note of that. It contradicts the flow of the other two vectors. So how do you write that? Good. We write R as being the sum of vector A and vector B. And how is it like that? Look at it. We have a vector that's coming like this. The vector is starting from here. ends here, we call it vector A. We have another vector starting from here, ending here, we call it vector B. Vector B. Now, and that one, this the vector B stop here. There's a vector that is now joining from beginning of this one, beginning of A to the end of B. That vector is summing A and B together. And look at it, the direction of it should start from the from point A to what? To point B. So that is what the main resultant for. So in this diagram, this represents the diagram very well. The resultant is of the vector equals to resultant vector equals to vector A plus vector B. Now we want to look at parallelogram law. Parallelogram law says that if two vectors at a point are represented in magnitude and direction by the adjacent side of a parallelogram, the resultant is represented in magnitude and direction by the diagonal of the parallelogram drawn from the common point. Good. You see, or sorry, I said draw from. We can say draw from the common point, or you can say passing through that point. Now, we know that this is a parallelogram. Look at this is a parallelogram. Now, in a parallelogram, we have two diagonals. Look at this is a diagonal. There's still another diagonal like this. Okay, so let me erase the second diagonal. Now, what the law is saying is this. If I now represent this side with a vector A, I represent this side with vector B, I represent this side with vector B, then the law says that this point that connects this vector to this place is the what? Resultant. Good. Now, you may be confused about what do they now mean by passing through that point. They are connected at a point. You'll be looking at how is vector A and B connected. But let me show you, because that is very, very important for you to get the concept perfectly. To get the concept perfectly. Now, you see how they are connected now. Now, look at this parallelogram. This is vector A. This is vector B. Can you see that they are connected at this point? This is their connection. But because this is a parallelogram, if this place is vector A, this place is also vector A. And this place is also what? Parallel to vector B is also vector what? B. But because we are interested, we are not interested in the whole of the parallelogram, we just need the triangle. Now, look at it now. If I'm now looking, I'm looking at this side now, I'm looking at this one and this one now. This is their common point. This is where the resultant is going to come out from. The resultant is going to come out from. Can you see? Resultant. So that's why the law says that if two vectors are at a point are represented in magnitude and direction by the adjacent side of a parallelogram, the resultant is represented in magnitude and direction by the diagonal of the parallelogram. You can say drawn from the common point or passing through that point, because we already said that if the two vectors are at a point, they're acting at a point. So now, what do you gain from this? What you get from this is that this triangle that we have here, if I erase this triangle that I have here, if I erase this, on that, good. Let me erase it. The agenda is too much. Now, let me use this to do that. If I cancel out this what, this side of this, can you see that the remaining one is like the triangle law? This is the resultant. Don't forget, it's like the triangle law. That's why I said earlier that the triangle law and the parallelogram law are actually talking about the same thing. Take note of that. So what do you gain from here now? How do you calculate our magnitude? From mathematics, we can get the magnitude of the vector, either from our parallelogram or from our parallelogram law, from our triangle law. We can get that the resultant magnitude of the resultant equals to, we can get that the magnitude of resultant equals to R equals to square root of A squared plus B squared plus 2AB cos theta. The cosine of theta, this theta is the angle between the two vectors. So we did some mathematical derivation to get it. But what is important for you is to be able to what? Recall and use the formula. Now, we are dealing with a vector, resultant. So we need the magnitude and we need the direction. So now the direction, if you after drawing a parallelogram and want to find the direction that the resultant vector that we found is making with the horizontal. So this is how we do it. Don't forget, you can see that this is b sine theta over a plus b cos theta. It is b that is having sine theta and it is b that is also having cos theta. One is at the top, sine is at the top, cosine is down, which is the normal order. If you want to find tan, sine over cosine. So that should make you remember that. And how do you know the vector that will be multiplied with sine theta and also with cosine theta? You can know that if you look at this. Let's look at this diagram. Can you see that there's one vector that is assumed to be horizontal, this one, vector A. Then this vector B is the one that is what? That is slanting. So is that vector that is slanting that will have the sine theta and also the one that will have the cosine theta. We're going to apply the formula so that you know the best way to what to apply it. So the next thing that we want to look at here, we want to look at vector resolution. One of the properties of vector is that a single vector can be what? Can be splitted into two. That's one of the beautiful things about vector. And it can be splitted into two perpendicular vectors. Look at this is a single vector. This is a single vector. I have angle theta here. This is a single vector. This vector can be brought to this direction and it will become vector px. That is vector p along the horizontal, x axis along the horizontal. I can also bring this vector up here and it will be what? Vector p along the vertical distance, along the vertical direction. I hope you are following the concept. Good. Now, students normally make mistake on how to resolve this. So I'm going to give you a trick that you use. That trick I created it for myself so that I will always remember when I'm using cosine and when I'm using sine. Look at this. If I'm bringing this arrow, if I'm trying to push this arrow down here, down this direction to the x side, if I'm trying to push it, I'm going to be compressing that angle. If I'm bringing it this direction, I'm going to be compressing this angle here. So compress, I use the C, that is going to be cosine. If I'm dragging this arrow to the y direction, it's like I'm spreading it. I'm going to be spreading this angle. If this angle happens to be a rubber band, if I'm pushing it down, I'm compressing it. But if or let's assume that it happens to be a spring, if I'm pushing this arrow down here, I'm compressing it. If I'm pushing this arrow to the y direction, I'm spreading it. So spread, use the word sine. S for sine here. Please take note. So that's why I have my px, p cosine theta, because along that direction, theta is being compressed. While along the y direction, p is being what? Spread. The reason is that why I'm telling you that is that you can have an examination question where they didn't put theta here, or you're not asked to find theta, and they give you another angle here, alpha. So let's assume that this is the angle they give to you. And you already memorize that when you are taking it to the horizontal is cosine, and when you are taking it to the vertical is sine. This should be wrong. So make use of the concept of compressing. The angle is like a spring. When you compress it, compress. C for compress, that's cosine. When you are pushing it towards spreading sine. So make use of that concept. It will make things very easy. Now, we can also solve, apart from using formula, we can also solve vectors using graph. So I'm going to quickly look that and we'll conclude the class today before we now look at examination question. Now, look at this vector now. I want to solve this thing on a graph book. It's very, very easy. 30 Newton and 40 Newton. I'm not going to bring scale. How can I plot 30 Newton and 40 Newton on my graph book. It's not possible. Then don't forget, I already assume that this is not the first time you are hearing about vector, because by now you ought to know that vector is represented by an arrow, and the length of that arrow, the length of the arrow will determine the magnitude of the vector. How big the vector is will be determined by the what? Length of the arrow. When the length is very long, then that vector is what has high value. When the length is small or short, then the vector is what? Is short vector. Look at it now. 40 Newton is a bit the 40 Newton is a bit longer than 30 Newton. Yeah. So because the length of this is more than this. So now let's see how we can solve this on our graph book. Good. Look at what I do there. I like, oh, this is 30 Newton, this is 40 Newton. Okay, let me assume that 10 Newton stands for 1 centimeter. I call it a scale. I assume that 10 Newton stands for 1 centimeter. So now I can measure this. I can just bring out my ruler. 30 Newton will mean 3 centimeters. I will draw a straight line that is 3 centimeters on my graph book. Then I will draw another line that is of 4 centimeters, because this is 40 Newton. So I draw the 4 centimeters on the horizontal. So now I will now use my ruler to join the top of this place to this. I join it, the straight line. Then I use my ruler to measure the length. When I measure the length, if this is properly done, you can try it at home. If this is properly done, I will get 5 centimeters. Now, 5 centimeters is like saying 5 times 1 centimeter. And you already know that, you already say 1 centimeter is standing for 10 Newton. So 5 times 1 centimeter is like 5 times 10 Newton. And your answer is going to be 50 Newton. If we apply formula to solve this vector, we are still going to get 50 Newton. So we are going to learn how to use the formula to solve this in our next video on vector. So thank you very much. Please go through this video once again, write the essential information in your book and make sure you understand it properly. Then you can proceed to the next video where you are going to learn how to apply these formulae that you have learned. Thank you very much for your attention. Thank you.